Okay, let's get started. So we're going through lab, somewhere in here, lab quiz and interview. So before I get into some more content, does anybody have questions about how this works or just wants me to go through a spiel? If nobody has questions, I'll just go through it. Okay, so this week we have quiz and interview. Some of you haven't had interviews, haven't had lab yet. We have Friday night labs for some reason. So we're still in the midst of this, but I just want to remind you how this works and what's going to happen, what to expect over the next little bit. So first, when we do have grades ready for you, they'll be posted on AutoLab. You can't see this lab quizzes yet, but there will be lab quizzes, lab interviews, and your results will be posted there, along with some feedback. You can click your score and get some feedback about what you need to prepare for the next round of interview or quiz. We'll get that back to you. We try to get it back as fast as possible, but things happen. The TAs are taking other classes. I got a lot of other stuff going on too. We try to get it as fast as I can. What I will say is that we'll get it back to you before next week's lab. So next week is Learning Objective 1 review, where you're going to go over the solutions to the version of the quiz you took in your lab section, and any questions you have for the TAs, anything else they can help you prepare for that makeup quiz, which will be 2 weeks from now. That second chance lab, which will be, again, the interview and the quiz. It'll have the same structure, same format as this week's lab. So I want to get results back to you before next week's lab. In each lab, results will come out on a rolling basis. So we're not releasing the results for the entire class all at one time. We'll release for each lab section so you can have your lab's results back before next week's lab. That's the feature we want. That's what we want, absolutely, for a turnaround in grading. Next week's lab is review lab. I want you to have results by then because, I won't tell you don't go to lab, but if you pass the interview and you pass the quiz, you can make an informed decision for yourself of whether you want to spend 2 hours reviewing something that you already passed and that you already know. Not going to hold it against you if you don't want to go to that. So I want to get your results so you can make that informed decision. Whereas if you didn't get credit for the quiz and you're pretty fuzzy on that stuff, please go to the review. There's nothing more frustrating than somebody who fails either the quiz or the interview, especially the quiz, because we do memory diagrams in the review lab. Fail the quiz, skips review, fails again, and then sends me an email. I'm really struggling with this class. What can I do? You could have went to the review lab. Nothing more frustrating than that. But unless you have a valid excuse to miss this lab. And then if you pass the interview and you pass the quiz, there's definitely no reason for you to go to this second chance lab. This one I will tell you to skip. We won't have anything for you there. Unless you want to take the quiz, take another quiz for fun. The TAs won't interview you. They won't call out your name. You won't be on their list of students to interview because you already passed the interview. So you definitely won't get an interview. You could do the quiz for fun, and then when we go to grade it, we'll be like, wait, they already have credit for this. Why the hell did they take it again? Plus, it maybe I shouldn't say this one, but it can cause confusion during grading. I've had, I think, just one student who took the second chance quiz after passing the first chance quiz. They passed it the first time, but actually failed it the second time. We didn't notice that they already had credit. Failed it the second time, so we updated their grade to 0. Of course, they earned credit. They emailed me. I changed it back to a 1 because it was an honest mistake. Because they already earned credit for it, so we're not going to change it to 0. But just in the logistics of handling a class of that semester is 400 students, it just didn't get caught at any point, so their grade updated to 0, and it was a big confusing mess. So there's only things to lose by taking the quiz again, is what I'll say. There's no reason to take the quiz twice. Or for extra practice. If you take it for extra practice, just don't submit it. That would be fine. But yeah, so that's what's up for lab. Nobody's going to take the quiz twice, though. One student out of hundreds, thousands. Nobody's going to do that, right? So the next 2 weeks of lab, if you pass the quiz and interview, no reason to go to those labs. The quiz has two different things that you can earn, the learning objective and the application objective. If you get the learning objective on the quiz and you passed the interview, but you didn't get the application objective on the quiz, there's still no reason to go to this lab. You can't earn the application objective on the second chance labs or any recovery opportunity quizzes. So I've said that a bunch of times. I can't say it often enough. I just want to make sure everybody knows that. Your opportunity to make up those AOs and get any AOs that you missed is all the way down here on the final exam. At the final exam, that's where you can catch up on those application objectives, any application objectives you missed on the first chance labs. You can't make them up on the second chance labs. Which I think is all the logistics for that I want to talk about. I said a lot of these things, like most of these things on day one, but that was forever ago. Now that it's actually upon us and it means a lot to you, do you have any questions? I wanted to repeat everything, but any questions on especially the logistics? Yes? So this came up in the other lecture too. I don't have a definitive answer, like this is how. So for quiz grading and interview grading, I guess, there's no scores, percentages, anything like that. They're pass-fail things reviewed by humans. We have a small team of TAs and myself. We're going to look at these things and decide if your submission proves that you've completed this sentence. Like, can you trace through a program and draw the memory diagram for a program with respect to the stack, with stack memory? If we can say, yeah, based on this submission, I'd say they can. Then absolutely you're going to get credit for it. The application objective is a little more vague. If you clearly understand the concept, if you just knock it out of the park, all three questions, you just nailed them, especially the third question. The third question is intentionally quite harder than the first two. That's so we have more information to go off of when determining the application objectives. If you nailed question 3, you're most likely getting the AO. But it's a case-by-case basis. We have to have human beings reviewing these things because it's all case-by-case. Not all errors are the same and everything. But you can make errors. If you make small mistakes, you can still get the application objective as long as those mistakes aren't fundamental to your understanding of tracing through a program and drawing the memory diagram. For the learning objective, it's a little easier to explain. We have these handful of concepts: adding variables to the stack, adding a stack frame to the stack, adding code blocks and removing code blocks from the stack, and having your input-output displayed on the memory diagram. There's only a handful of real core concepts that we've learned for memory diagrams. So if any one of those concepts you just clearly blanked on, say you have no idea, like all your code blocks are completely jacked up or something, you're not going to get the learning objective. But if you do pretty okay on every concept, and maybe question 3 is pretty trash, you didn't really understand that one, but questions 1 and 2, you showed that, hey, look, I can trace through a program. My arrow was a little off or something, but I got the idea. We want to give you the learning objective. So you can make quite a few mistakes and still get the learning objective, as long as those mistakes aren't fundamental misunderstandings of stack frames, code blocks, putting variables on the stack, and you got your I/O. Honestly, if you miss your I/O, the output, and that is your only mistake, I still want to give you the learning objective. That might rule you out of the application objective, though. But they're all case-by-case decisions. You make a lot of little mistakes, do those little mistakes add up to a misunderstanding of this sentence? You can't actually trace through things? I don't know. If they're all really silly mistakes, or if they're cascading mistakes, this is why we can't really have a rubric for these things and say you lose 2 points each time you have the wrong value in a variable. Because what if the very first variable in your method, you made one tiny mathematical error which cascaded to all of your variables having the wrong values throughout the program? Well, it's only one mistake. I want to give you the learning objective. If it was just one mathematical mistake, I'm not testing your mathematical ability here. I'm testing your stack frame ability. I still want to give you the LO and probably the AO as well, even though technically you made like 20 mistakes. So not all mistakes are equal, and we want to review those manually and decide for ourselves whether it's a fundamental misunderstanding or a silly mistake. The unfortunate downside of that is I can't say, well, if you get over an 80%, it's an application. I can't really give you a solid, concrete answer like that. I have to be a little bit vague. Yes? Yes. Yeah, so if we can answer this in the affirmative, you pass the quiz. If we can answer this in the affirmative, you pass the interview. If we can answer this in the affirmative and you just like confidently like, yes, they absolutely understand this, then you're getting the application objective. And for the interview, there's a little bit more specificity I can get. There's 3 clear topics that you were asked about on the interview. Unit testing, or will be asked on the interview. I spoiled this before anybody took the interview, so nobody's getting an advantage for me saying this right now. Unit testing, stack frames, and variable scoping are like the 3 core topics that I talked about in lecture after we finished talking about Scala syntax. So if one of those 3 topics you just completely bombed, say the TA asked about unit testing, and you're like, I know the hell out of unit testing. Stack frames, I know the hell out of stack frames. Then it got to variable scoping with code blocks, and you're like, oh, I don't remember how that works. Well, that's one of those 3 topics that you just didn't know. Unfortunately, that's going to be a fail, and you got to retake that interview. So the interviews, we are looking, did you understand all of these topics? Where in the interview itself, stack memory is kind of broken down into stack frame and variable scoping. Both of those are encompassed inside stack memory. But on the other hand, if those 3 topics, like your answers were pretty okay in all 3 categories, that's probably going to be a pass. If for unit testing, for example, you're asked like, what's up with unit testing? And you're like, oh yeah, it's a way to automate testing. It's, I can't go too far because then it would be given the Tonight Labs an advantage. But and then you're asked a further question, like how do we compare doubles? This one I'll give, I guess, because I talked about doubles forever. You're asked about comparing doubles, and you say, well, we have to compare using an epsilon. There's some truncation errors, like you can't fit the whole number in a computer or something like that. But I don't really understand the details. Like we just had to use epsilon in our code, something like that. That's a pretty okay answer. Like I'd like more details, but it's not terrible. It's not bad. It's all correct. It just could use more. And your answers for variable scoping and stack frames are of that similar magnitude. Like you pretty much got what's going on, but not in super great detail. I want to call that a pass. So you don't have to like knock every question out of the park, but you should be doing at least pretty good on every category of question. Even if there's a whole question where you're like, I don't know, that could still be a pass, depending on which question you say that to. Like you're asked about comparing doubles, and then the TA asked about comparing dictionaries, and you're like, dictionaries, I'm thinking Python. Maps, and you're just like, oh shit, I don't really remember about maps, and I'm still working on task 3, so I really haven't messed around with that. And the rest of the interview, you get every question pretty good. That still might be a pass. Again, it's human reviewed. We look at the submission, each TA, when you were getting your interview, the TA was frantically typing all kinds of stuff. They're dictating what you said, and then we're going to review those and decide if what you said is enough to constitute a pass on the interview. We're not looking for perfection. We're not looking you to be at a level where you could be down here teaching the class. We're not asking that, but you have to have a pretty good grasp on the concepts. And not be missing an entire concept. If you got the rest, great, but unit testing, you're like, I don't know, I just do it so Autolab shuts up. That's not a good answer. That's a retake. And keep in mind, when these grades do start coming out, failing in the quiz or interview isn't that big of a deal. You just take it again in 2 weeks. Failing that one is a little bit bigger deal, but you just use a recovery opportunity and get another chance. Once you start digging into those recovery opportunities, it starts getting scarier, it starts getting dicier. But before then, there's really no reason to sweat quite yet. Go to the review lab, brush up on what you need to, take it again in 2 weeks, pass it, you'll be good to go. All right, any other questions on this? We're in the first stressful part of the semester, so I want to make sure it's all out there. And I understand that this part is really stressful because you have no idea how we grade these things. I can explain it as best I can, but there is some subjectivity in the grading, which we usually don't have in computer science, so I know it's tough. Stuff for me, stuff for the TAs, it's stuff for you. But once we get through the first round of this, hopefully your nerves settle down a bit once you understand how the grading works. Or you get more stressed out if you fail them, I guess. Hopefully that doesn't happen too much, but we'll get through it. You'll take the second chance, and it'll be fine. Okay, let's get into content. So the slides are here. If the slides don't show up, hit it with a refresh, and they'll show up. I pushed them earlier today, so if you didn't refresh the page as of a few hours ago, you might not see them there. Just refresh, and they'll be there. Okay, we're going to talk about merge sort today. Whenever I talk about merge sort, I preface it with, I guess, a cautionary tale. I don't know what to call this. But you're going to see merge sort quite a few times throughout at least through your academic career. As instructors, we love merge sort. It helps us teach a lot of different topics, so you're going to see it a lot. You've already seen it in 115. Ever so briefly. Hopefully they're still doing that, and I'm not just making that up. But at the very least we used to. I'm pretty sure they still do. But it comes and goes. It's like a brief flash, like here's merge sort, ain't that neat? And then they move on to the next thing. You're going to see it again right now. You're going to see it again in 250. And you're going to see it again in 331, and probably in some other classes. I don't know. Some other classes probably want to probably use this as well. When you see merge sort, each of the 4 times I mentioned, we're using merge sort to show you a new thing, a new concept, a new topic. So in 115, it was kind of, here's a high-level overview of sorting. Hey, here's one way we can sort, but there's a faster way, merge sort, that can do n log n. Ain't that cool? And then we move on. In 116, I'm going to use it to explain recursion. So I'm going to explain actually how this algorithm works. It makes 2 recursive calls. Like, is that just magic? No, it's recursion. We're going to talk about it. When you see it in 250, it's going to be used to show runtime analysis, and you're going to actually prove mathematically that the algorithm is n log n. It's big O of n log n. I'm not going to talk about runtime so much today, but in 250, I'm not going to steal their thunder. They're going to talk about it extensively. And then in 331, and I think 250 does a little bit of this these days, 331 is going to take merge sort and use it to show proofs of correctness. How do we know that merge sort is correct on every single possible input that it could ever be given? As of right now and after 331 in your careers, you're going to write unit tests, give it some inputs, check the outputs, and if it passes on that handful of inputs that you came up with, you're going to be like, I'm feeling good about that. I think it's right. And then push it to production and let users use it. In 331, you're going to actually write mathematical proofs that there does not exist any possible input for which the algorithm is incorrect. It is correct on every single input ever. And you prove it mathematically, like the most comprehensive unit test suite you could ever imagine, an actual proof of correctness. So each time you see merge sort, we're using it as a vehicle to usher in a new topic, recursion today. So don't make this mistake I did. This is where it becomes a cautionary tale. Don't make the mistake I did. By the time I got to 331, and Autry was the instructor, and he's like, we're going to learn merge sort again. And I'm like, I've learned merge sort like 3 times at least by now. I got this, and I just checked out. And then some point through the lecture, I zoned back in, and he's like halfway through a proof of correctness. I'm like, what the hell is this? Is this merge sort? And I missed quite a bit of that lecture because I'm like, merge sort again? Come on, man. We're not reteaching merge sort 4 times. We're always adding it and using it as a vehicle, like I said. We do that because, one, sorting is really easy to understand. Before you ever learned anything about programming, you knew what sorting was. It's a very intuitive thing. We as humans have sorted things all the time. We like when things are sorted, at least in certain instances, certain circumstances. So you know what the problem to be solved is, and we can focus on the solution to that problem. And two, merge sort carries a lot of cool topics with it. It's an algorithm that sorts. It uses recursion, which brings up some nice runtime analysis and proof of correctness analysis. How do you prove correctness on a recursive algorithm? It brings up a lot of nice topics pretty naturally and a pretty compact algorithm. The algorithm itself isn't that complex, so it's just one we really like. Just want to give you that cautionary statement. Don't space out when you see merge sort. So the algorithm itself, I said it's pretty simple and it can fit on a slide. At least at a high level, we'll look at the code in a bit and look at the details of how this works. But at a high level, this is it. It's a recursive algorithm where the base case is if the list has 1 or less elements. Technically, if somebody gives us an input of the empty list, we're going to return the empty list. But if it has 1 element or the empty list, just return it. It's already sorted. If the list isn't clearly already sorted by just having 1 element, we're going to split the list in half and make recursive calls on each half. Now, last time I said I like to get my recursive calls 1 small step closer to the base case. And in general, I like that, but not always. Here we are going to do something different for the purposes of runtime. So splitting this in half just gives us a lot better runtime. We could just peel off 1 element, but we're not going to get to our n log n that way, since that is the end goal of merge sort. So for what it's worth, if I was just trying to get the job done, I would just peel off 1 element and send the rest to the recursive call. And we'd end up something similar to selection sort in the end. We're going to recursively call on each of those halves. Each of those halves are getting closer to the base case because we split the input in half. And then we're going to merge those lists back into 1 sorted list. Importantly, we're going to assume that our recursive calls are correct. We're going to assume that each half of the list was sorted, and then we're going to merge 2 sorted lists into 1 larger sorted list. That's the algorithm. That's merge sort. Obviously, there's a lot of details in there, and we'll talk about those. But at a high level, that's the algorithm. Visually, if I want to sort this list of size 8, and yes, I chose 8 because it's a power of 2 and it all divides evenly. If you have an odd number of elements, in your code, you would arbitrarily choose how to split it up. You would split it as close to in half as possible. This one that will split exactly in half, so my slide's nice and symmetric. Split it in half. We didn't hit the base case. Split it in half and make recursive calls on each half. So we're going to make a recursive call to merge sort on each half of this list. Each recursive call says, is this the base case? No. So we're going to make 2 recursive calls, split it in half again. Each recursive call is going to say, is this a base case? No. Split it in half again. And make recursive calls of size 1. We repeat that until every recursive call is going to hit the base case. Now we have 8 lists of size 1. And we can sort these. We just return them. They're already sorted. And then where the actual sorting, where the algorithm kicks in, is when we're merging 2 sorted lists. So when we get our recursive calls and we say, okay, I'm going to assume these 2 lists are sorted, and my task is to merge them into a single sorted list, that's where we're doing some work. So we're going to say this 1 is less than the 51, so the 1 goes first. This 19 is less than the 100, so the 19 is going to go first in the merge list. 2, then 8, 3, then 4. So now we have larger lists that are all sorted, and we're going to merge those together. So this recursive call was waiting for the 2 recursive calls when it was split, and it's going to merge these. 1 and 51, 19, and 100. Merge these. Take the 1, take the 19, take the 51, take the 100, take the 2, the 3, the 4, the 8, and merge those lists together. And now the top level recursive call gets these two lists of size 4 that are both sorted and merges them into the final result, a list of size 8 that's all completely sorted. That's visually how the algorithm's working. And finally, let's see the code. Or any questions yet on this? I think Nicholas is answering the ones in chat. Fine with that answer? All right, let's see the code. So a lot of the code is in this merge method. That's a method that I wrote. We'll see that in a few slides. But first, let's see the top level, how merge sort the code is working. So we get an input list that we want to sort. We're going to check if it's the base case. I'm just going to say if less than 2. So if it's either the empty list or a list of just one element, I'm just going to return it. You give me a list of size 1 or 0, it's already sorted. Why are you even asking me anything? Just return it. Done. I like my base cases as simple as possible. I don't want to do any work in my base case. I want to do at least the very minimal work required. In this case, I'm returning the input. I can't think of anything more straightforward than that. Just return the input. Wednesday, I was just returning 0. I want as simple as possible a base case because I don't want to accidentally make any mistakes in the base case. Accidentally, I guess I wouldn't make a mistake on purpose, would I? I don't want to make any mistakes in the base case. If it's as simple as possible, it reduces the potential for bugs in the base case. And then else, if we're not in the base case, we hit the recursive step. I'm going to split the list in half. So a few things here. This is one instance where I'm actually taking advantage of integer division. So usually I say this as, hey, avoid integer division, make sure you don't have integer division. This time I'm leveraging it and taking advantage of it. So I have input data.length, which is an integer, over 2, which is an integer. I'm not writing 2.0, which would be a double. I just have 2 with no decimal. That's an integer, and I'm storing the result in a variable of type int just to make sure that this thing is an int. So this is integer division. If the length is odd, say the length is 11, which we'll see a length 11 list in the code. Actually, no, it's going to be length 10. I'll have to change it to 11. This will be, if this is 11 divided by 2, the result is 5.5. The 0.5 gets truncated, and I get 5 as a result, as the midpoint. Then in the next line, I'm going to use this split at method, and don't panic if this notation scares you a little bit. I wouldn't expect you to do this on your homework. You can, by all means, use it, but it wouldn't be a requirement on anything. I wouldn't say you have to understand this stuff. So if you don't understand it, don't panic. Focus on the rest of the course, the rest of the stuff. I just did this so I can do this all in one line, but I use this split at method, which takes an index and returns a pair of lists, which I can assign using this parenthesis syntax to declare and assign 2 variables in the same line, which unpacks the pair. The split at returns one thing, but it's a pair, and I can unpack that pair with this syntax into 2 variables. Left and right, where left contains all the values before this index, and right contains all the values at and after this index. So the midpoint index itself goes on the right-hand side. If I had a 0.0 on there, I believe I would get an error, or would it just be a warning? I forget. I haven't tried that in a long time. If you try to, so if it's 2.0, you would get 5.5 in my example, but you would get a double, more importantly. It would be of type double, and you try to assign that to an int. I generally avoid that, but I'd forget what Scala does in that case. If it truncates for you and autocasts it to an int, or if it just gives you an error. Either way, you might not get what you want. It's better to be careful about that and make sure you're just assigning ints to ints so you don't lose precision when you would prefer to have the decimal place. Maybe you accidentally wrote int instead of double. I prefer that Scala just says, hey, you can't do that. But I don't recall what it actually does. So we have our left and right and make our recursive calls. We're calling merge sort, which is the method that we're defining. We're currently defining. We haven't even finished explaining this method. There's more code over here, but we're going to call it before we even get to that code. So 2 recursive calls on the left and right. We're going to assume that the recursive calls return the expected values. So these are copies of left and right, but in sorted order. And we still haven't really done anything. We just split this list in half. So now it's time to actually do something. We need to call merge, or we need to merge these lists. I did it in a separate method. But we need to merge these 2 lists into a single list in sorted order. While we do this, we're going to strongly leverage the fact that these 2 inputs are sorted. Merge will assume that those 2 lists are sorted. If they're not sorted, our merge code isn't going to work right. It's not going to do the right thing. So our task is to merge 2 sorted lists. It's important that the inputs are sorted, or else the algorithm we're going to talk about wouldn't work. And if we wrote a general merge that merges 2 unsorted lists into sorted order, well, that task would basically be write a sorting algorithm, and there would be no point in setting up merge sort at all if we had that power in merge, assuming we could do it in nlog n. So we want to merge 2 sorted lists. To do this, take advantage of the fact that the inputs are sorted. This won't work if they're not sorted. We're going to start at the beginning of each list. We're going to compare the first element of each list, and whichever one comes first, copy that into an output list and advance to the next element of that list. Repeat the process until you reach the end of one of the 2 lists. When you reach the end of one of them, take everything that's left in the other and copy it into the output. So that's how we want to merge visually. It looks like this. We want to merge these 2 lists, our last 2 lists from the previous example. We're going to start by looking at the first element of each list. Decide which one goes first, which is going to be, of course, 1 in this case. Copy that one to the output and advance that pointer, advance to the next element of that list. And then repeat the process. 19 verse 2, well, 2 is going to come first. 19 verse 3, 3 is going to go first. 19 verse 4, 4 is going to go first. 19 verse 8, 8 is going to go first. We reach the end of this list, so we're just going to copy everything else from this list over to the output. And that's going to give us a merged list with all the elements in sorted order. The code, there's a good chunk of code here. I should warn you before I just shock you with a bunch of code on a slide. But I maintain that this code isn't overly complex. I'll run through it quickly. I get 2 lists. I'm going to assume that they are sorted. I'm going to start by looking at the index 0 of each list. I'm going to set up my return list where I'm going to store all of these sorted values after merging. And I'm going to hit a while loop. While loops, I think they still skip these in 115 as of last semester. I think this semester we're adding them back in. But while is going to have the same syntax as an if, except it's going to loop until the condition is false. So as long as this condition is true, it's going to keep looping. Once this is false, it's going to break out of the loop and continue down here. So it's like the combination of a for loop and an if statement, a while loop. So while this Boolean condition, this Boolean expression is true, execute this code. This Boolean expression is saying if left pointer is less than left.length, which means if left pointer has already looked at the entire left list, and, or I said that backwards. Well, left pointer isn't at the end of the list, and right pointer isn't at the end of its list, keep looping. So this loop is going to execute until one of the 2 pointers reach the end of its respective list. This loop is going to check, this is the only actual comparison that's made in this algorithm, it's going to check which element goes first. By comparison, I mean the only time we're ever actually caring about the order of the elements. With all this code, all this recursion and everything, there's only one line that says these two elements, which one goes first? It's the only time we're actually sorting. So we're going to say the value that the left pointer is pointing to, and the value that the right pointer is pointing to, is the left one less? If so, append the value that the left pointer is looking at in the left list, append that to our result list and reassign it, and advance that pointer by 1. So copy that element that we're looking at on the left list to the output, and then advance to the next element in the left list. Else, for what it's worth, ties I'm pushing to the right. Else, do the same thing but on the right. Copy the right element to the output and advance that pointer by 1. This breaks once we hit the end of one of the lists, and then we got to clean up. If we're not at the end of the left list, copy things from the left. While we're not at the end of the right list, copy things from the right, and then return our overall result. For anyone who's very astute, really paying attention, which I would assume is somewhere between 0 and 1 of you, this isn't an n-log-n implementation. So just in case somebody is seeing that, this is not an n-log-n implementation. This is much slower than n-log-n. I believe it's n squared, or worse, it might even be n cubed. So if anybody's itching to call me out on that, I'm going to call myself out. We'll actually learn why by the end of the semester when we talk about linked lists. But I just want to give that caution. Or if somebody's watching this on YouTube, some software engineer like, oh, I wonder what Jesse's doing. Hey, that's not n-log-n. It's not. I'm not claiming it to be. The algorithm is n-log-n. My implementation of it is so terrible here that it's not n-log-n. All right, so writing a recursive method, we followed these steps. We wrote a base case with trivial input-output behavior. If you give me a list that's trivially already sorted, length 0 or length 1, just returning it. My recursive step, all my recursive calls must get closer to the base case. I'm splitting this list by 2 and then making the 2 recursive calls on the 2 halves. This is always going to be true when the input is length greater than 1. And if it were not length greater than 1, it would hit our base case. So the fact that we're in the else, I have a list of at least length 2. So when I split this in half, even if it's an odd number, each half is going to be smaller than the initial input. For example, that wouldn't be true if the input was size 1. We would have one empty list and one list of size 1, and we're not getting closer to anything. Like if our base case was an empty list, we would never get there. Since our base case is 0 or 1, we have 2 or greater, we're going to split it in half, we're always getting smaller. So we're getting closer to the base case, so we're not going to hit infinite recursion. We're going to assume that those calls will return sorted lists with the values that I gave them, and then we're going to base our logic of our algorithm around the assumption that the recursive calls are correct. So if those 2 recursive calls gave us sorted lists, we're going to merge them where merge is assuming that the inputs are already sorted, which is our assumption from our recursive calls. And then we're going to return a combined list with all of the values sorted. And merge is going to enforce that our assumption is correct. So our assumption will start off being correct when these are the base case. When we have the base case, we just get lists of size 1. Merge is going to merge them into lists of size 2. And then once we have lists of size 2, merge is going to merge them, make sure it returns the correct thing, and then on an input of size 4, it's getting 2 lists of size 2, which are sorted, our assumption is correct, and then merge those together. As long as merge is doing what it's supposed to be doing, that assumption is going to be correct when it returns. So that call of size 8 that made 2 calls of size 4, well, it's going to do the same thing. And merge is going to enforce that all the way up, that assumption is true. And it's trivially true for the base case. Our logic in merge is making it true for every other case, starting with the base case and going all the way up. Let's mess around with the debugger. I want to change this, I guess. So this merge sort, if you don't see this code, again, pull, and it should show up in the recursion in LO1 program execution. This code did exist, but in LO3, I rearranged some things and got this into LO1. So if you don't see that, just pull. So let's do some more debugger. Already have it running. Oh. All right, so with the debugger, again, for now, I'm always going to set my breakpoint at the first line of main so we can just trace the execution of a whole program. And then I'm going to run in debug mode. I'm going to run the debugger, and it's going to run my code until it hits a breakpoint. Which is going to be pretty quick, well, after compilation, because it's the very first line. When it stops at a breakpoint, it stops before that line is executed. I saw this question in chat, but I had missed it during lecture on Wednesday. It stops before the line is executed. So run merge sort did not even begin starting yet. The breakpoint is kind of like right above that line. So all we have on the stack is this and args, two things that we don't worry about in 116, and we don't add on our memory diagrams for the purposes of reducing clutter. But we can see each stack frame over here, and then when we click on a stack frame, we see all of the variables in that frame. I'm going to step into to get into my run merge sort method. And again, there's going to be some code that I wouldn't expect you to understand. If you want to explore this, it's fine. If you do understand it, that's great. But you're not expected to understand like this and this. It's just stuff we used to teach in this course, but we cut because we just weren't seeing the benefits from it. But this line, suffice to say that this is going to generate a random list of doubles for me, ranging from negative 0.5 to 0.5. So I have n equals 11 in this stack frame. I'm going to skip over this line, and that's going to give me this numbers, a list of doubles that are just going to be random values. I wanted to call merge sort. I need something to sort, so I'm just generating a random list of stuff to sort. And we're going to call merge sort. Just to show you where we're at. Merge sort, this is what we saw in lecture. Merge, this is all what we saw in lecture. And then I have generating a list, calling merge sort, and then just printing out the values to the screen so we can see that they were sorted. And then in main, just calling my run merge sort. So inside merge sort, we're going to have input data. I can never resize this just right. We're going to have merge sort has input data, which is that list of size 11 that we created. Definitely not the base case. So we're going to split this in half. We're going to have 11 divided by 2, integer division, so the 5.5 gets truncated to 5. Split at mid is going to give us two lists, left and right, with all the same values, but split into two lists, one of size 5 and one of size 6. Then we're going to make a recursive call on the left list. Left list does not hit the base case. It's got 5 elements. So do the same thing. 5 divided by 2 is going to be 2 with integer division. Split it in half, make a recursive call. We got a list of size 2. And we got it's a 50-50 shot in both lectures that happen. The first element is, it's already sorted. But it's not the base case. Split it in half. So we have 2 lists of size 1. And we're finally going to hit our base case. At this point, we have quite a few frames on the stack. This recursive call added a lot of frames to the stack. And we can go back and look at them, see what the variables are in every stack frame. Makes the debugger a very useful tool. We can see everything that's happening in the program at any point in time. Very helpful to debug your programs. This time we did hit the base case. So we're just going to return this list that we were given. We hit the base case again on the right side. But just to show you more debugger stuff, I'm going to use step over. I don't want to go into merge sort again just to say, oh, it returns the base case. So I'm going to skip over that one. We have these 2 lists of size 1. Nothing to sort. But now we have to merge these two lists. They were already in sorted order, so it's a little less exciting. We can go through merge, but I kind of don't want to go through merge with just two lists of size 1. It's just going to go through all the overhead without really computing anything. So I'm going to step out of this and then advance. And we go, that stack frame returns, and we go back up to this stack frame that had these two lists that it needs to sort. Left, it already was sorted, but now it's certainly sorted. And again, I'm going to skip over the right recursive call. It's going to make 2 recursive calls of size 1 and 2. It's going to end up making 3 calls to the base case and merging small lists. I'm going to skip over that one too. Just so we can talk about merge with a little bit more interesting example. We have a list of size 2 and a list of size 3. My God, are they? Oh, yeah. Never mind. I was going to say, are they actually sorted? They have to be sorted at this point. That's my bad. And then we're going to go through this with these 2 lists. So left pointer equals 0, right pointer equals 0. Get those on the stack. Sorted list, where our result's going to go, get that on the stack. And then start doing our comparisons. As long as we're not at the end of one of these 2 lists, make a comparison. Oh, no. And I'm going to set a breakpoint since the debugger's been weird with my loops lately on Wednesday. I'm going to set a breakpoint here just to make sure it stops inside this loop and doesn't skip over my loop like it had a tendency to do on Wednesday and on Monday. So I'm going to advance. When it tells me, do you want to go into length or length? I don't want either of those, so I'm going to skip over it. It's going to hit my breakpoint. If it was going to miss it, it should have went in there anyway, but things get weird sometimes. Left pointer, left versus right. First element in both. We have 0 and 0, so the index 0 of both. Negative 09, negative 08. So we expect the 09 to be put into the output list. So we're going to copy that into the output. We have negative 09. And this pointer, the left pointer, advanced and is now looking at index 1 of the left list. We'll do it again. This time we hit the else because we're looking at negative 08 and positive 32. Negative 08 is going to be copied and advance the right pointer. Now we're comparing element 1 of each. The right will go again. Try to click through this one a little quicker. The right will go again. So now right, we're at the end of the list. Right pointer is 3, size is 3. So when we check our conditional, this is going to be false, and we're going to break out of this loop. And we copied all of the right list already over into the output. Break out of this loop. Oh, son of a bitch. And we end up below that loop where our other code was. We're going to check the left, copy everything else from the left over to the output. This was already false. Skip it, and then return that sorted list up to the next recursive call. So this is the debugger. It can really help you on your homework. The lecture question, I'll still show it, but I forgot to upload the form that has A, B, D, or C, so it's only file inputs. Just submit any file, and you'll get the lecture question. Submit anything as a file, and you'll get the points. But this is what was supposed to be the lecture question. I messed up the form. The other lecture already went through it with free points, so I got to give you free points as well.